In the previous video, we described what is perhaps the easiest way to simulate a quantum circuit using Qiskit, and that is by using some of the classes available in the quantum info module. So for example, we created a circuit, and by using the state vector class, we were able to get the state at the output of that circuit, and by using some of the methods from that state vector object, we were capable of extracting, for example, the ideal probabilities or sampling from that state vector to emulate as if we were performing measurements on that state. Now, one of the issues we run into is that the quantum info package does not allow for us to include measurements when we're going to, for example, extract the state vector. So if we want to implement a circuit like this one, where a measurement is made and the result is used to apply another gate, then we will get an error saying that we can't really implement that state vector. So for that, we need to switch to a different type of simulator. And in this particular video, we're going to cover the basic simulator. So this used to be known as the basic air simulator, but it has been renamed. And the main difference is that even though it is an inefficient simulator, it will allow us to implement circuits that have mid-circuit measurements. So let's go ahead and basically just copy the circuit we had above, and then let's import from Qiskit the quantum circuit class to make sure we can't run this cell, and also from Qiskit providers and then basic simulator, or basic provider rather, we can import the basic simulator that we're going to be using. So first let's create that simulator object, and let's call it, for example, simulator basic. And now let's just go ahead and run this cell with the circuit again so we can see what we're trying to simulate. So the first thing we typically do is we create what is known as a job. And to create a job, we take that basic simulator object and we use the run method, to which we're going to pass the circuit we want to simulate and basically the number of shots we want to run. This job, once it executes, then we'll have a result stored in it. So if we do here .result, we're going to be able to store it in this variable. And then we can go ahead and, for example, print a result. And we'll see that there's a lot of information stored in there. For example, the qubits, the number of qubits in our circuit, and the size of the registers, and so on. But somewhere in here is going to be the count of executing this circuit 1,024 times. Now, luckily for us, there's a helper method called getCounts that we can use to extract the results from this circuit. And then if we print those, we can see that we got about half of the time state 1, 1, and about half of the time state 0, 0, which is what we expected from this circuit. Now, similar to the counts that we will get from the state vector class when we use the sample counts method, this dictionary comes already in a format that allows us to use the plot histogram or the plot distribution function from Qiskit visualization to get a nice result. Now, in a similar way to what the get memory method does for the state vector class, we can use the basic simulator to emulate the sampling of the circuit and return the results from each execution. And for that, we again use this run method. We pass the circuit, we pass the number of shots. Now let's do only 10 for this case. And then we need to set this parameter memory equal to true. And then everything else stays the same as what we did here. So basically we just store our result, job.result, and then we can get our samples by using result. And then here, instead of doing get counts, we do get memory. And then we can print our samples. And here we can see that the first time we executed the circuit, we got 0, 0, the next one 1, 1, 0, 0, and so on. Now, an important thing about using this type of simulators in Qiskit is that they usually rely on a set of basic gates they can simulate. So if we, for example, import, let's say, the quantum Fourier transform circuit from the Qiskit circuit library, and let's say we implement a circuit with, let's say, 3 qubits and 3 classical registers, or 3 classical bits, and append this QFT object to our circuit, and then just measure all of our qubits, we see we get a circuit that will just perform the quantum Fourier transform and then perform the measurement. Now, what happens when we try to simulate this using the basic simulator? So let's pause our circuit with some number of shots. And here what we can see is that we get an error that basically says that our simulator does not recognize the QFT operation. That's because this QFT is not part of the basis gates that the simulator can run. So for this reason, what we need to do is to always transpile our circuits. And what transpiling means is taking a certain type of circuit, like for example here the QFT, and translating it into gates that whatever simulator or other backend we're going to use understands and can run. So we're going to do from Qiskit, import the transpile function. We're going to create another circuit, let's call it QC sub t. That is just basically the transpile version of our circuit, but we need to specify which backend to use, which is going to be our basic simulator in this case. And now if we try to execute that job again, but now passing this new transpile circuit, let's say same number of shots, we see that there's no error anymore, and then we can extract our result by doing job.result and then get our counts by doing result.getCounts. And then let's print that, and we can see now that the circuit has executed correctly. So it's very important that we always transpile our circuit to avoid this type of errors. So as we can see here, this basic simulator allows us to execute circuits with mid-circuit measurements, unlike the state vector class in which we couldn't do that before. So in summary, we use the basic simulator when we need to find counts or samples of a circuit that has mid-circuit measurements. However, we shouldn't use the basic simulator if our circuits are too large, because as I said, this is an inefficient implementation of a simulator. Also, if we need to find, let's say, the coherent state at the output of the circuit, we can't do it with the basic simulator. What I mean by this is that we can extract the results stored in the classical registers, like the number of counts or the samples that we get, but we can't get the state vector even after the measurement has projected that result. Also, if we need to add noise, we can't do it with the basic simulator. Now, all of these 3 issues are addressed by the next simulator we're going to cover, which is the air simulator. So in the next video, we'll go into the details of how to use that and discuss the different features it has.